Now we will look at the estimation and loss minimization portion of this exam, corresponding to problems 22 to 24. So we're given this loss function L of theta and x, which returns 4 times the difference of theta and x when theta is greater than x, and the difference of x and theta when theta is less than x. Okay, so this is very similar to the absolute loss. In fact, it's exactly the absolute loss if we were to ignore this 4. Okay, this problem was actually discussed in discussion 5 of this semester, fall 2018, which I will link the solutions to below, but we will still go over this question now. So first, is this function concave or convex? So it might help to draw what this function looks like. So it'll look very similar to the absolute loss. The slopes will be slightly different, but that doesn't really change the shape of it. It's something like this, okay? Something like that, okay? And this function is indeed convex, okay? Because any secant line that I draw between any 2 points on this function will either be on the function or above it. Okay, so if I pick 2 points that are on the same half of the function, like for example these 2 points or these 2 points, of course the secant line will be exactly on the function. But if I pick 2 points that are on different halves, the secant line will be above the function. So either way, that satisfies the definition of convexity. So if it's convex, in this case, it's clearly not concave, right? Because if a function is purely linear, then it's both convex and concave, but that's not the case here. Is this function smooth? No, because there's a point here at the very corner, right? And so it's not differentiable at that corner. So the function is not smooth. So the only correct option for this first part is the second one, that it's convex. Now, given a sample of x1 to xn, what is the value of theta that minimizes the average loss? Show your work. Okay, so let's take a look. So we know, I guess first we can differentiate our loss function with respect to theta. And again, since loss function is piecewise, the derivative will also be piecewise. It's equal to 4 in the case where theta is greater than or equal to x. And it's equal to -1 in the case where theta is less than x. Right? Now, if I take my loss to be my sum of losses for all i's, right, all I going from 1 to n of the loss of theta and xi, my derivative of my loss, and this is the same process that we've done numerous times, both in lecture, discussion, lab, and homework. If I take the derivative of my loss, I'll be left with a sum of these derivatives, right? So the sum of dl by d theta evaluated at x1. Okay? So this sum right here will have n terms, all of which are either 4 or -1, right? It will be 4 for the terms where theta is greater than or equal to x. We can say xi. And it will be equal to -1 when theta is less than xi. Okay, so we can break apart our original sum, going from I is equal 1 to n, to being 2 separate sums. One of the value 4 for when theta is greater than xi, and one of the value -1 for when theta is less than xi. Since we're trying to optimize this, we can set this equal to 0. And with a little rearranging, we can write this as 4 times the number of xi's that are less than theta is equal to the number of xi's that are greater than theta, right? Because this count, the sum of 1, where, for example, theta is greater than or equal to xi, this is the same as the number of xi's that are less than or equal to theta. There should be equal to there. Because if we're just counting 1 every time some certain property is true, it's just the number of elements for which that property is true. Okay? So what this statement reads in English is the number of xi's that are greater than theta is 4 times more than the number of xi's that are less than theta. So if we draw out this real number line and put theta somewhere, what it's saying is there's 4 times as many values to the right than there are to the left. Okay? I.e., 1/5 of the values are less than theta and 4/5 of the values are greater than theta. I.e., this is the number at the 20th percentile. Therefore, the value of theta that minimizes the average loss is, in fact, the 20th percentile. Okay, and again, this was also done in discussion 5. Solutions are linked below if you have more questions. The optimal value theta star is a percentile for the population or the sample. Well, in this case, it's the sample, right? Because we are told that we have a sample x1 to xn. We just have some n data points, not necessarily a good estimate of the sample. Now in question 23, we're given the simple model y is equal to theta star and some data set of the 4 points 0, 2, 4, and 10. And we're asked to interpret the following plots. So it should be pretty clear that the plot on the left represents squared loss, i.e. L2 loss, and the plot on the right represents absolute loss. Right, and of course we're looking at average. And just as a refresher, the optimal value of theta for squared loss is the mean of our data set, and the absolute loss, the corresponding value, is the median. And these are things that we've all done in lecture discussion. Okay, so which choices for theta minimizes the average square loss? Well, it's the mean of the data set, which is 16 over 4, which is 4. We can also see that visually. Which choice for theta minimizes the average absolute loss? Well, it's any value that's in between the two medians, right, which are 2 and 4, because we have an even number of values, but also visually, the numbers 2 to 4 have the lowest loss. So it's 2, 3, and 4. Now, in part 3, we're told that suppose we add an observation y5 is equal to 100. Which choices of theta would minimize the average absolute loss? Well, now if our points are 0, 2, 4, 10, and 100, the median is precisely 4. Okay? Because for average absolute loss, the minimizing value is the median. And part 4, we're sort of given this general question, which loss function is most sensitive to outliers? The answer to that is squared loss. And this is something we've seen in lecture many times. And the reason for that is because in squared loss, all of the residuals sort of are squared, as opposed to absolute loss, where it's just the absolute value of them, and the Huber loss, where it's some combination in between them. Okay? Now in 24, we're asked to find the theta that minimizes the following loss function for some data set of points that look like xi, comma yi. Okay, again, this is something that we've also done in discussion, but we will represent here. Okay, so we can take the derivative of our loss function with respect to theta, and we're still left with the sum going from I is equal 1 to n of 2 yi minus theta xi times negative xi. Okay, because there's a constant term being multiplied by theta, and that's a negative xi. Okay? I can rewrite this sum, distributing the negative sign as the sum going from I is equal 1 to n of theta xi squared minus xi yi. Okay, and I can pull this 2 out in front. So I can write it like that. And I'm setting this equal to 0 because I'm trying to optimize for theta. So I can ignore the 2 because I can divide both sides by 2 and distribute this sum. So this will give me the sum of I is equal 1 to n of theta xi squared minus the sum from I going 1 to n of xi yi is equal to 0. But if it's equal to 0, I can just subtract the second term over, and I can say that these two sums should be equal. Now, we notice that theta is a constant term, so I can pull theta out in front, and I have theta times the sum of xi squared is equal to the sum of xi yi. And now dividing both sides by the sum of xi squared, I get that the optimal theta is the sum xi yi over the sum xi squared. Is that one of our options? Yes, that's precisely the second one. Oop, that wasn't that clear. Right here. Okay, so that's the theta that optimizes this given loss function. And it looks like that wraps up our exam walkthrough for the fall 2017 version of this exam. So if you have any questions, feel free to post on Piazza, and good luck studying.